Swayam Prabha. Digital India. Educated India.
It's a continuation of my previous lecture, okay, where I was trying to tell you some interesting things about our differential geometry, okay, and at least the interesting title of the lecture is rainbows and gears, and so this is these are disparate things. The rainbow is something that you see in the sky, okay, and gears are mechanical things that are used to basically transmit rotation, change the axis of rotation or change the sense of rotation, okay. Now how are they connected? So this is the common thing is differential geometry, okay, and it's the idea of curvature, okay. And so to begin with, let me say a few things. The first thing is let me tell you about the idea of curvature, okay. So curvature of a plane curve, okay. So there is this curvature of a plane curve. So what is this? Basically you are looking at a curve on a plane, okay. So when you say curve in general, it is you can imagine it in a plane, which is like drawing a curve on a piece of paper. Then you can also have curves in space, okay. For example, a helix, the DNA is a double helix, okay. So you can have a helix which is a curve in space. And then more importantly, there are curves on surfaces. You can imagine, for example, all the curves you can draw on a sphere, okay. Literally whatever we are doing, whatever movements we make on the ground, they are actually movements on the sphere. So we are actually tracing curves on the sphere, and they are space curves, okay. So, and then of course you can also have curves in n-dimensional space, okay. So mathematics allows you to think beyond 3 dimensions. So you can have an n-dimensional space, and of course n-dimensional space is kind of imaginary in the sense that you cannot visualize it, but the point is it's actually real in the sense that, for example, if you want to have a unified field theory or something like that, for example, there is something called string theory which needs 10 dimensions, okay. Relativity needs 4 dimensions, it needs x, y, z space coordinates, and you also have a time coordinate, so it's 4 dimensions. So you see, so you need more dimensions actually, though the only problem is that beyond the 3rd dimension you cannot imagine anything, okay. But then the point is, if you can't see in higher dimensions, what do you do? So there are these devices in mathematics which are called devices of topology, devices of linear algebra, devices of calculus. This is what makes you to imagine in higher dimensions and make statements in higher dimensions, even though, so you have some intuition, and then you know how things behave in 2 dimensions, you know how things behave in 3 dimensions. So you generalize that and you get a mathematical intuition, and using that intuition and using the required mathematics, the mathematics that is involved are basically 3 fields of mathematics. One is called topology, which is actually the study of continuity. Then you have the mathematics of linear algebra, which is study of linear maps, which is in simple words study of matrices. And then the third thing is differential geometry, which is basically calculus, okay, which is called manifold theory, okay. So so the point is that we are when you study, you first study curves on a plane, then you study curves in space, 3 space, then you can generalize it to curves on surfaces and curves in n-dimensional space, okay. So the first thing is, how do you understand what is meant by curvature of a plane curve, okay. So the idea is as follows. So what you do is that you have a standard model for curvature, for constant curvature. So there are 2 standard models. One is a straight line, the curvature is 0, okay. And then you have the idea of a circle. A curvature is constant for a circle, okay. And what you can understand is that if the radius of the circle is r, okay, The curvature is the extent to which the circle is curved, okay, and you can see that as r goes to infinity, as r becomes larger and larger, your circle is less curved. That means what you can understand is that the curvature is inversely proportional to r. Okay. So you can see that, so you can write, so what we do is that we take the constant of proportionality to be 1, and then we simply write k equal to 1 by r. That is the formula we take. Okay. And why is this correct in a philosophical sense? If you let r to tend to infinity, your circle becomes a straight line. A straight line is considered as a circle with center at infinity or radius infinity. Okay. And then 1 by r, as r tends to infinity, 1 by r goes to 0. So straight line has curvature 0. So these two are consistent. Okay. So the moral of the story is that how do you measure constant curvature? By looking at a circle. Okay. Now how do you do this for a curve? So this is a question that was posed by Newton, and it was answered by him because it requires calculus. Okay. So basically the idea is like this, and it's a very standard question in physics, in kinematics. You know that when a particle is moving in a circle, okay, you know very well that if it is moving with the tangential velocity v and the radius is r, and the mass is m, okay, then the centripetal force is mv squared by r, that, okay. And of course, the centripetal force is directed, to the towards the center of the circle, okay. So it is in the minus r cap, okay, where r cap is is r vector by r, mod r, which is just r vector by r, okay. So the centripetal force is kind of acting towards the center of the circle. So this is the centripetal acceleration, and if you forget the mass, then it's basically v squared by r, okay. And the question is that this is the case of uniform circular motion of a particle, okay. Now the question is, what if suppose what is the most general kind of motion? You have something moving on a curve, okay, on a plane curve, okay. So what happens is that you have a particle moving on a plane curve like this, right? And then the question is, how do you describe this? How do you describe this? How do you describe this motion? This motion has you must understand that it has two components. One is there is also translation, because you are covering distance. At the same time, there is also rotation. At every point there is rotation and translation. Now the point is that you can somehow try to separate this and study the rotational aspect. If you concentrate at a point, this is called instantaneous, okay. So what happens exactly at that point of time, okay. At given a point of time, the particle is at some point on the curve. At that point, how do you study the circular motion? So the idea is that you can fit. So how do you define curvature? Basically, the circular motion at this point is connected with the extent to which the curve is curved at that point, and that should be the curvature of the curve, okay. Now how do you get this curvature? There are three ways of doing it, okay. So let me call this point as P, okay. Then this curvature of the curve gamma, so I will call this is the curve capital gamma at the point P. It can be defined in three ways. One is the so called geometric way, the other is the so called let me say analytic way, and there is a third way of doing it, and this is the so called calculus way, right. And so I will tell you the geometric way, and I will very briefly tell you about the calculus and the analytic ways, because probably you are not introduced to calculus. So what is the geometric way? The geometric way is very easy. Basically what you do is, you see what is the standard model for curvature? It's a circle, okay. So all you have to do is, at this given point, you try to compare the curve to a circle passing through that point, okay. And what circles will you take through that point? Not all circles. They should be they should be circles which touch the curve at the point. So basically what happens is, this curve has a tangent vector at that point. This is the tangent vector to the curve at the point. And then you look at all possible circles which touch this curve, which means that those circles will also have the same tangent. So basically what you do is, you look at you look at a circle like this, and mind you, unfortunately my circle is not so neat. So here's a green one, and then I can draw another one, say a red one. Okay, I can draw various circles. All right, and of course I can draw them on both sides, but I draw them on the side in which the curve is curved. All right, and then the point is that you try to get a best fitting circle. Now, what is the meaning of this best fitting circle? The best fitting circle is a circle that very close to the point, you see the circle should approximate the curve maximum with minimum error to the maximum extent. Okay, that is the best fitting circle. Okay, and you find that best fitting circle and you take its radius, then you take the reciprocal of the radius. We have agreed that's the curvature, and that's how you get the curvature. So what happens is that you get this purple guy here. This purple guy here is the best fitting circle, and then I'll call it as CP. All right, and this is called the circle of curvature.
So how do we decide that it's the best fitting?
Good question. So I'll tell you. Yeah. So I will come to that. I'll come to that. So that is the next question. So you find a best fitting circle, and then what you do, that's called the circle of curvature. Then it has a point, a center, and that is called the OP. This is the center of curvature. Okay, and this circle has a radius, so you can imagine this will be 90 degrees to this tangent. Okay, that will be a common tangent to both the circle and the curve at that point. And this radius, you will get this, if I call this as P, then you have this, you get this R, so I will call it as rho. Okay, rho P. This rho P is actually this distance, so rho P is actually the distance POP, and the curvature at the point P, so curvature is given by kappa, so I will use kappa, which is just Greek K. Kappa at P is just 1 by rho P. Okay, so this is the curvature. This is the curvature function. Okay, and you can see that you see this curve, as the curve becomes flatter, this circle becomes bigger, and and if the curve is very sharp, then the circle becomes very small. The curvature increases. Okay, so that's how it is. Now the question is, how do you get this best fitting guy? To that so this is a geometric way of looking at curvature, but there is this question of what is meant by best fitting. And of course, this best fitting, as you asked, you can actually do the following thing. What you can do is, I can compare the distances between very close to this point. I can compare the distance between the curve, points on the curve to points on the circle in the normal direction. And basically I want that distance to be minimum. I want it to be minimized. Okay, so the distance between the curve and the distance between the circle close to the point in the normal direction, I want that to be minimum. That should be the way to get the best fitting circle. Okay, I mean, I want a curve that kind of infinitesimally as you go very, very close, that approximates the curve to the maximum extent. So you can see that this is some kind of a limiting procedure. Basically what I can do is, see what is it what am I trying to say? I am trying to say the following thing. I am saying that see, for example, you take, so this is, so let me show this. So you see, this is the so you see, this is the curve, the way I have drawn it. Wait a minute. So this is my curve. All right, and then what I do is, suppose I take this red line, take this red circle, then of course this is supposed to be a single point. Okay, what you do is that along the normal direction you measure. All right, you measure in the norm. So the normal direction is this normal to the tangent direction. Okay, you measure the distances, and so if it is this red one, this is what you will measure. If it is the green one, well, you will measure this. Okay, and then if the blue one, you measure. So you measure the distances, and you have to kind of see, the problem is that you have to go very close as possible, so that you get the best fitting circle. Now this is where an idea of limit comes. So you can guess that you can't do this without using some limiting argument, which means that you'll have to get to calculus. Okay,
so in this case the green one
No, I mean don't, my picture is not to scale, okay. So this is just a, this is an imaginary kind of picture, okay. So in principle this is doable, but the problem is that how far will you zoom in to, do this, and where do you stop? There is no stopping, because I can take a smaller and smaller and smaller portion of the curve around that point and zoom it and keep doing this. So the answer to these kind of questions is calculus, okay. So you have to use calculus. Now, but this is the geometric idea, alright, and the point is that, of course, you can ask, why should this best fitting circle ever exist? It exists actually, and you have to prove it using calculus, okay. So there is a limiting argument. So I will tell you, so that is so I come to this calculus part. So what is the calculus part? So the calculus part is like this. So the calculus part is done in the following way. You have a question.
Wouldn't the best fitting circle basically just be the largest circle which you can fit, such that it's only its tangent? Because if you go larger than that, it'll start intersecting. But if you go smaller, it'll start contracting, and the distances will become larger. So the best fitting circle should be the largest circle you can fit, which is still tangent to the curve.
No, but in principle, I can, if you just look at that, if you take a line, if you want suppose I fix a line and take a point on that, okay, and I can look at circles through that point which have that line as tangent. I can literally make the circles as large as I want. It doesn't end, right?
No, but then like if you zoom out, it'll start intersecting the curve in other places. No.
We are, mind you, this is only at that point. You don't care about how the curve. It is independent of how the curve turns at other points. See, this is that's why it's a, it is an infinitesimal. It is a instantaneous kind of trying to understand what is happening at that point. You are not bothered about if the curve is turning in a funny way anywhere. You are only worried about a very, very small neighborhood of the point. Okay, so you are not looking at it globally. So see, there is this zooming that you have to do, but the point is how much you are going to zoom. There is no control over that, and that means it's a limiting process. And the only way you can control all these limiting processes is you have to use calculus. Okay, so when you do calculus, so I will tell you what is the calculus method. It's very, very easy. See, basically what you do is you have the curve. You take it is just like, how do you get the tangent to the curve? Basically what you do is you take a point, you take a nearby point, draw the chord, and then make this nearby point come closer and closer to this, then the chord becomes a tangent, right? So basically what you do is you take the point P, and then you take nearby point P prime, or let me call it as Q, okay? And you know pretty well that, if you take this chord as Q tends to P, then this chord PQ will become the tangent at P, okay? As Q tends to P, chord PQ tends to tangent at P. So this is how you would have done it in calculus, okay? So, but anyway, you don't need calculus for that. This is just common sense, right? Mind you, P is fixed, Q is moving, all right? Now, what you do is, how do you get the circle? So here is something amazing that's happening. What you do is, at the point P, see what you see from this picture is that, see, you want to find this circle of curvature. There is only one thing you know from this picture. I don't know the radius of the circle, but I know two things. I know that it is having this tangent as the tangent at that point. The circle passes through that point. It has a tangent as that. That means the radius lies on the normal to that tangent at that point. Okay, that is a normal to the curve. And somewhere in the normal, there is going to be this special point, which is the center of curvature. Once you find that special point, its distance, that normal distance to that point where you are taking the tangent, that is the radius of curvature. So the point is to nail down that point center of curvature. That's called the center of curvature. Okay, that is the whole point. Now how will you do it? So what you do is, so the idea is again very, very simple. What you do is, at the point P, you have the tangent. Okay, then you draw the normal to this. Okay, so this is a normal at P. Okay, then you take a nearby point Q. Again, at the point Q, you are going to have a tangent at Q, and you are going to have a normal at Q. Okay, and these two guys, they intersect at a point. Now you know what we are going to do. You try to take the limit as Q tends to P, and then this intersecting point, I call it a CPQ. This will tend to the center of curvature OP as q tends to p. You should, so you see there's somewhat of a, there's something here that is funny that's going on. See, as q tends to p, the tangent to q will also tend to tangent to p, okay, because I am assuming the curve is a smooth curve. That means the tangent is varying continuously smooth curve. So assume everything is continuous and nice, okay. Then what happens is, you see this NQ and NP, they are going to become literally, they are going to merge. Then you see, you will not be surprised if this point CPQ goes to infinity. See, after all, it's the same line, right? As it comes closer and closer, it looks like this point CPQ may go away to infinity, right? But it doesn't happen. So that's the beauty. You have to use calculus to show that the CPQ goes to a finite limit, and that limit is the that point that you're going to get by calculus. That is the center of curvature. So now what you'll have to do is, now you have to translate all. You can write the equations of those lines by analytic geometry. You can write their slopes. Then you can use calculus to calculate this, and you can get the calculus formulas for the center of curvature, radius of curvature, and so on. So this is the calculus method of doing it. Okay. So the idea is that, basically the center of curvature is kind of, you take nearby normals and take the limit. That's your center of curvature. Okay, that's the idea. Okay. So now, of course, I think I have told to my project students. I don't know whether whether they discuss with you, but you are also welcome to discuss with them. There is a book. The book that I gave is Andrew Presley, Elementary Differential Geometry. It's a very nice book to read. Okay. And I think you were asking me about somebody. Was it you or was it the other girl? For a good calculus book. Oh, it was you. Okay. So, I have a recommendation for a good calculus book that you can read. That will help you even if you go to college. And it's a book. It's a very, very simply written book. It's very good. It's good for physics and engineering. So the name of the book is, it's famous. It's called Piskunow's Calculus. Okay, Piskunov, Piskunov, Piskunov. So it has 2 volumes: differential calculus and integral calculus. It's written in excellently beautiful, simple language. Okay, and it has a wide coverage of calculus that you need for, university and engineering, all undergraduate stuff. Okay, you have all the calculus that you need. So you can read that book. Okay, so that's a good book if you want to. It's a long-term, very readable book. It has calculus in one variable, then it has multivariable calculus. It has differential equations. Then you have also other advanced topics like, Fourier series and things like that. Okay, it's a very good book. Okay, so let me get back. So it is Piskunov Calculus, and it's actually 2 volumes. So this is one book for calculus. My other favorite is, of course, as I told you, is Andrew Presley. Elementary Differential Geometry. Okay. So these are very nice books to read. Right? Yes, you got it. Yeah. Piskunov is also available. It's a very famous book. I think it was translated when I was born. So it's a very old book. Okay, so it's a classic. It's very nice to read. All right. Okay, so you see. So let me get back. So you see, I already told you what is the geometric idea of getting the center of curvature and the circle of curvature. The taking the limit part is done by calculus. So you take nearby normals and then you try to take a limit, you get the center of curvature. Okay, and then from the center of curvature you take the normal segment to the point where you have drawn the tangent. That is your radius of curvature. Taking inverse of that will give you the curvature. That's all. It's as simple as. But what you must understand is the curvature is a function, because the curvature depends on the point. If you change the point, then this k. That's why I have written as kappa of p. Kappa of p, because it's a function of the point on the curve. Okay, you have to understand that, right? Then there's one more thing I will tell you about, which is analytic. It's kind of analytic and algebraic at the same time. Why is it analytic and algebraic? Is because you are trying to approximate to a circle which is a second degree algebraic equation, right? X squared plus y squared plus 2gx plus 2fy plus c equal to 0 with g squared plus f squared plus c positive, g squared plus f squared minus c is positive, and then you also have that is a radius squared, right? So therefore the moral of the story is that this is for people who you will learn this. Every object that is nicely differentiable, okay, has what is called a Taylor expansion, okay, and what happens is that this curve has a Taylor expansion, and what you are trying to find out. So if you write the Taylor expansion, there is a first derivative part which is a tangent, then there is a second derivative part, okay, then there is a third derivative part, okay. Now what you want is, if you truncate it in the second derivative part, you will get the equation of this circle, okay. So basically, how do you get the best fitting circle? It is the second degree Taylor approximation of the curve, okay, that is the way to see it, alright. So that is the analytic or algebraic way of doing it, okay. So let me not go more into this, but I want to tell you the following thing. So you know what is the center of curvature. Now yes, your question, yes.
Sir, how do you find Taylor series for random curves?
For
Random curves, like any curve, given curve, how do I find the Taylor series?
Yeah, that's a good question. I mean, you have to write out you write the curve as a function of one variable, because it's and then in that one variable,
then we can use Taylor's theorem.
Then you use Taylor's theorem, that's all. See, for example, if you take a circle, center let us say 0, center 0, and let us say radius let us say r, okay, then this is x minus x naught though, so here this is x squared plus y squared equal to r squared. Now and r is of course 1, so x squared plus y squared equal to 1. Then the point is that this is a curve. How will you say that this is a curve? Because it can be parameterized by a single parameter. You can put the parameter as theta, 0 less than or equal to theta less than or equal to 2 pi, then you can put x equal to cos theta, y equal to sin theta, okay. Therefore a point on the curve is cos theta sin theta. Now what you can do is cos theta can be expanded into a Taylor series, 1 minus theta squared by factorial 2 plus etc. Sin theta can be expanded to Taylor series, and that's how you get the Taylor series. So it's basically now you have two coordinates which depend on single parameter. They are two functions. You have to write the Taylor series, and then you have to interpret it all as vectors, okay. So you have to rewrite everything using some vector algebra.
Sir,
so it's basically Taylor series of function of two variables, but the two variables are actually one variable, because the two variable point is moving on a curve which is actually one parameter, all right, okay.
Sir, do we have a method by which we can write any given curve as a function in some variables?
That depends on what is your definition of curve.
No, because some curves are like continuous, like they can have a given function which denotes whole of that curve, but some cannot be done like that.
No, of course you have to put conditions on the curve, okay, and then so this is the topic of what is called as implicit function theorem in manifold theory. So when can you write it out in a nice way? How can you write? When is an implicit function going to define an explicit curve? What are the conditions for that? So this is a multivariable calculus question. It's called the implicit function theorem. So this is a very general question, okay. But I don't want to get into that at the moment. You can look at any, for example, you can look at any multivariable calculus and look at the implicit function theorem. That is the theorem that that will answer your question.
Sir,
okay.
One more doubt, sir.
Yes.
You gave it this way. Can we express any curve in its parametric form and then write the Taylor series for it?
Yeah, of course. You can do that, of course. That's exactly what I said. You can do that. Except that now you have to write the curve as, xi plus yj. So it will become cos theta I plus sin theta j. And in the cos theta I, you put the cos theta Taylor expansion. Sin theta j, you put the sin theta Taylor expansion, and then write it in I and j. Okay. So yeah. So now let me. So what is it that we have seen? You have curve, and you have the idea of curvature, and you have a circle of curvature. At every point there is a circle of curvature. There is a center of curvature. Okay. Now from this curve we are going to. So I am trying to get to this how are rainbows and how are gears connected. Okay. So yes.
Sir, Sir, all these calculations are for curves which are drawn on a plane surface which is completely flat. What will happen if you bend that plane surface? How will the curvature change? Curvature of that curve, which is like on a let's say a hyperbolic surface, will it change, or with respect to the?
Yeah, it's a good question. So first of all, the root. So he is asking about space curves, in particular about curves which are lying on a surface, right? But in general, you can ask about space curves. Now the point is, for a space curve, how do you define curvature? That's a separate story. Okay, I'll come to that. Okay, I'll come to that. So since you asked it, that's also, it's not a bad idea that I tell you what it is. Okay, so this is what you do for a space for a plane curve. How will you do it for a space curve? So let me explain that. Since you asked that, it's also probably the right time to say. So you see, let me take a space curve and say let us say in 3D. In 3D, there is that means in arc 3. Okay. So you see you take something like like a helix. Think of a helix. Now what is happening is that if you take a point on the curve, okay, this curve is moving in space now, or it's no longer in a plane. So now what do you mean by curvature? Okay. So again, what I can do is that you see in the plane what happened. If you give me a point on the curve, I have tangent, and then I can take the best fitting circle, and I have a calculus way of getting the best fitting circle. That will give me the circle of curvature. Its center is the center of curvature, and its radius is the radius of curvature, reciprocal of which is the curvature. Everything is nice. The problem with the space curve is that there is no plane. Okay, what happens is, in a space curve you have a tangent. You have of course a tangent vector. Okay, the problem is that this tangent vector does not give you any special plane. There are so many planes which if you take a line in 3 space, there are so many planes that that pass through that line, right? In all 360 degrees you rotate. Take any plane, you can rotate it, okay, about that line. So there is no particular plane available for you. Okay, so if a plane is available for you, then what you could have done is, in that plane, you can try to get an approximating circle. But here again something amazing happens. What really happens is that you do the same calculus procedure. What you do is that you take this point, and then what you do is that you draw the normal at this point. Okay, so you draw the normal at this point. Okay, then what you do is you for all practical purposes, at least try to take 2 or 3 points, okay, so that there are no redundancies. So what you do is you take another point, let us say q1, and you take another point before and after q2. What you do is at q1 again, you have tangent, okay, and you have a normal. So let me draw this. So you have this normal at q1, and then there is also a normal at q2. And of course there are the tangents at q1 and q2. So so this is a tangent at q1, this is tangent at q2. And now what you must understand is that it's somewhat messy, because these are all lines which are in space, okay, and whether they intersect and all we don't know, because lines in space can be skew lines, all right. But again what happens is that you take these lines, there are 3 lines. Pairwise each of these lines determine a plane, and you get 3 planes. In general, 3 planes, if they intersect correctly, they will intersect at a point. Okay, that's because 2 planes will intersect in a line. Okay, and you will get 3 lines, and there are 3 lines which can accurately pass through a point. And believe it or not, it really happens. So if you let the q1 and q2 tend to p, okay, amazingly, okay, all of them coincide and you get a point. Okay, all the 3 planes hit at one point. It happens even in space, and this is again you have to prove it using calculus. Okay, and sometimes there are redundancies when you may have to use 3 or maybe even 4 points depending, but the point is you will get a consistent limiting point. So actually what happens is, once you do the calculus procedure, everything works, you actually end up getting a plane. So the amazing thing is the calculus procedure works, and you end up getting a particular plane through which the tangent line passes, and that plane is called the osculating plane. That is a very special plane, and in that osculating plane what happens is that you get a circle. That circle will be the circle of curvature, okay, and that circle will have a center, and that will be the center of curvature, okay. And of course, once you know that, you have this, you get the radius of curvature at the point, and then you can write the curvature at the point to be reciprocal of radius of curvature at that point. So the point is, this whole calculus stuff works if you do it properly, okay. What is so special is that it is only this calculus stuff that gives you this special plane which contains a tangent vector called the osculating plane. In principle, there are an infinitude of planes that contain a given line, but you get a particular plane, okay, and that is called the osculating plane, okay. And that, so even for a space curve, you get a plane, a very special plane containing the tangent vector, that's called the oscillating plane. In that plane you get a special best approximating circle, that is the osculating circle. Its radius is the radius of curvature, and reciprocal of that is giving you the curvature of the curve at that point, okay. Then, but the problem is, what this thing does is that it gives you only how the curve is turning along that plane, but the point is why it's called osculating plane, because the plane itself is changing. That's the whole point. As the point moves, this plane will start oscillating, it will start fluctuating, okay. So there is a tendency of the curve. So what is the difference between a plane curve and a space curve? In the space curve, there is in the plane curve, you see the curve is only in the plane, there is no motion perpendicular to the plane, okay. Whereas in the space curve case, there is a motion perpendicular to the plane, and that motion also leads to a new kind of curvature, it's called torsion, okay. So basically what you do is that you have this plane has, so at this point, if I draw it, draw another picture, so here is your curve, okay. Can you wait until I just finish this? So you see, you have this curve, you have this point, this is a tangent vector, the tangent at that point. Now there is a tangent plane here, this is the osculating plane, and then there is the circle of curvature, and then there is a center of curvature, okay. And then you have this so-called, so this is a normal direction, so this is 90 degrees, okay. Now there is a third normal, and so I'll write this as normal at the point, and then there is a third normal, this is perpendicular to both of these guys, and this is called the binormal at that point. It is the normal to the osculating plane, and somehow that is the vertical motion. See, why is the curve not in a plane? It's always trying to run out of its plane, that because of a vertical motion in the binormal direction, all right. And if you try to understand what is, so there's one more point of this that I so this is the right time to say it. See, I told you originally, if you are looking at a circle, then the radius of curvature reciprocal is the curvature, and what is the, if you look at it how do you get the curvature from physics? What is the centripetal force? Magnitude is mv squared by r. You put m equal to 1, you get v squared by r. Make v 1, that means you make the curve to be unit speed, okay. Making the curve unit speed means what? You are traveling around a circle with unit speed. Remember, that is uniform circular motion, but velocity is changing. The magnitude is the same, but the direction is changing, okay. So it's not constant velocity, it's constant speed. If you make v equal to 1, what happens to the modulus of this? It becomes 1 by r, which is the curvature. Therefore, moral of the story is, there is another important thing, another physical meaning for curvature. You travel unit speed on the curve, your acceleration is exactly your curvature, okay. The curvature of curve at every point is nothing but you make sure you travel unit speed on the curve and measure your acceleration. That's your curvature, okay. So for a unit speed curve, acceleration is just the curvature, okay. And now you can understand what I'm going to say. I'm going to say that, you know, I told you that there is a for a space curve, there is a oscillating plane, there is a tangent, there is a normal, there is a binormal. The binormal points outside the oscillating plane. Now if you try to measure the acceleration of the binormal, that is the vertical motion which is pushing the curve outside its plane all the time. That is what is making it move in space. For a plane curve it will be 0, so it will remain in a plane. For a non-plane curve, for a space curve, it will be non-zero, and that is going to be your measure of what is called as torsion. It is called the second curvature. So a space curve is controlled by two things. It is controlled by the acceleration. If you travel unit speed, there is the acceleration, which is a curvature. Then you are going to get something called torsion. And torsion and curvature, they are the things that control all the data for space curves. Okay, so that is the idea. Okay, so now questions. Yes.
Sir, do you define the curvature of a space curve as the curvature of the curve in its oscillating plane?
No. The curve is not in a plane first.
No. Like after we find the oscillating plane.
Yeah, you find the oscillating
then the
plane.
curvature we find, we define it the curvature of that curve at that point.
You define so the definition is you find the oscillating plane, find the oscillating circle. In fact, there is something called oscillating sphere actually. Okay, because it's 3D. You find the radius of the sphere and take reciprocal. That is your actually the curvature. That is the definition.
Sir, one more.
But you can also. But the point is that you have to do this. If you want exact formulas, you have to do it using calculus. So it's calculus, vector calculus kind of thing. But except that vector calculus is just scalar components, and you do the calculus on the scalar components.
Sir, and you told normal NP and NQ tend to each other, then we'll get one point which like will find us. Sir, like if they are collinear, then obviously we'll find multiple points. But how should we write the differential or use calculus?
No. You are asking for the method that
yes.
yeah. So that is
such
something
that they tend to each other and they intersect to the particular.
Yeah. That's a derivation that has to be done. Okay. So I don't have the time here to do that. But you can look at it. It's available on the web. If you search for it, you can write it down. So you have to write. It is the usual way you write. You have to write the point. You have to parameterize the curve with t. So the point p naught will be parameterized with t naught. Nearby point will be written as t naught, parameter value t naught plus delta t, and you have to write everything in terms of delta t, and then take limit delta t tends to 0. You have to make when you take the limit, always you have to be very careful. You have to divide by the right things and then take limit, because if you directly take limit, you will get 0 equal to 0. You will not get anything.
Sir,
so it's a big derivation. It takes some time.
Sir, so we can take parametric points and make the parametric points tend to each other, and then find the normals at those parametric points, and then find their intersection.
Absolutely. So any calculation that you do with curves, you have to first parameterize them, because you need a variable on the curve